All right, so coming back in to do the notes, kind of practicing the derivatives on the calculator using the n-derive function. And just a reminder that if you have the classic calculator of the TI versions, the classic calculators are going to be using the notation where you choose the n-derive, and it's under the math menu in Math 8, and you put your function, the variable that you're going to be taking the derivative with respect to, typically x in most of the problems on your calculator, and then the value of x at which you would like to know what the derivative is. So you would type it in like that. Those of you that have the newer version of the calculator will be using the kind of more traditional notation that is also acceptable on the AP, that the derivative with respect to x of your function evaluated at x equal to c. So they kind of show the same thing, but depending on your calculator, on the new calculators, you fill in these three spots. On the old calculators, you have to fill in the inside portion of the n-derive command. Also kind of reminding you that I might not have talked about this in every class, but we can graph derivatives. It won't give us a formula for a derivative on your calculator. These will only give you the values. This would be f prime of c, a specific slope, one value, a specific value, that we can, however, even though we can't get a formula from our calculator, we can ask the calculator to graph our derivatives by changing one item into our command, and that item is right here. Instead of putting a specific number here, you leave it as x, and what the calculator will then do when it's graphing is every x value in the table that it has, it goes and gets a y value and finds the slope and then calculates and plots the slope because it's a connect the dot grapher. So just to kind of show you a couple of examples, let's pull up our calculator here. And I'll use the example that was at the beginning of 3.1 notes again, just to kind of refresh everybody's memory. So here's my calculator. Let me make it larger. Here's the function, and I have it in y equals 3x minus x squared. And notice I'm using the newer version of the calculator, so the newer versions of the calculator use the derivative notation over here. I put in the derivative with respect to x of y1, and I did evaluate it at x equal to x. And what that will do, which we already know what this derivative is because we did it in the notes, it's going to be 3 minus 2x, that when I take a look at my graph, and you do have to wait just a little bit because it's doing a calculation of every point for every x value, but eventually you will see our derivative come across here. And as you can see from our derivative, that it comes across here at -3 has the y-intercept, and we went down 3 and over 1.5. And down 3 and over 1.5 is going to be a slope of -2. So the equation of this line, which is my f prime of x, was going to be my, I don't know why I put -3 there, positive 3 minus 2x. So that's the equation of the derivative, given that f of x was 3x minus x squared. So while we might not have been able to come up with the actual formula, the calculator will not give us this formula over here, but what it will do is it will graph a derivative for you. And this is actually something kind of nice as you're learning how derivatives are related to their original functions, that what you want to do is kind of play around with the calculator and work with it. Now remember that the calculator is using the symmetric difference quotient. All right, so derivatives on the calculator uses the symmetric difference quotient, and that symmetric difference quotient is great in that when we are calculating a derivative, like the example that we were doing, at x equal to 1, we want the slope of this tangent line. It uses points equidistant on either side, and then draws the secant line and use that secant line slope to estimate the slope of the tangent line that we're looking for. And that's usually a pretty good estimate, that this symmetric difference quotient is not really dependent on how close I am. If we do it the other way, which was you pick a point an h distance away, here's c plus h, that when I use this secant line as an estimate, it's not really a great estimate until h gets really, really close to 0. And so that's kind of why the calculator typically uses the symmetric difference quotient to calculate the derivative on the calculator, because you can be pretty far away and get a really great estimate of a derivative. And that's what the calculator is giving you, an estimate of the slope of the tangent line. Now we have some concerns and some cautions, okay? So let's take a look. We're going to evaluate this f prime of 4, and we're going to do it at ln of x. So one of the things when you're doing this, I kind of like to have down here in my second one the derivative with respect to x of y1. I just leave that in there, and I just keep changing my y1 so I don't have to keep redoing this. If I want to look at it graphically, let's put in our log function. And a couple of things to be concerned about with our log function is to remember that we started having a discussion that the symmetric difference quotient, based on the fact that it's using 2 points on either side and it's not using this actual point, that it does have some concerns. That the symmetric difference quotient is only good if your function is going to meet those hurdles for differentiability, that the function is continuous. And then after you make sure that the function is continuous, then the next step in kind of your flow chart of differentiability is to make sure your function is smooth. And what we mean by that is it doesn't have any cusp. And then after you make sure your function is smooth, then you check and make sure that your function does not have any vertical tangent lines. Function does not have vertical tangent lines, because those would have undefined slope. And so there's some couple of hurdles that you have to kind of meet, and you have to be careful of this when you're evaluating functions and finding them with your calculator. So taking a look at this on the calculator, okay, I'm just going to do zoom 6 and do a nice graph. And so the first graph you'll see is my log graph, and hopefully you'll recognize that, remember, log graphs, they kind of look like they end right here, but we have to remember that the log graph itself has a asymptote there. So as we're working on these graphs and you have the log graph, that this graph is going to continue. So even if you don't see it on the calculator, it might be a little hard to see that this really continues kind of running down parallel to this, that we have a vertical asymptote here. And if I was going to draw the derivative, kind of understanding why the derivative of the log graph, it ends up being this shape. First off, when you look at the slopes of all of the tangent lines coming across here, the first thing is to recognize that all of the slopes of the tangent lines, they're always positive. Okay, so first your slopes are positive. So that's important to make a note as to why this is the graph. The second thing that we want to make a note is we want to talk about the behavior, because we know there's a vertical asymptote here. We know that there is no derivative for x less than or equal to 0. You have a regional discontinuity down here, and we have an infinite discontinuity at x equal to 0. Now, I'd like to see what's happening on my slopes, so I start to ask myself the question, as x heads to 0 on the right side, I would like to know what the slopes are doing, f prime. Now, make sure kind of as you're asking this question, I know the function itself, the log graph, is going down. But what I'm asking about are the slopes. This slope is a positive slope. The slope over here, as x gets closer to 0, is a steeper positive slope. And the closer I get to 0, the steeper the positive slope will be. And so therefore the slopes are going to infinity. And notice that here on our derivative graph of this function, it's showing the exhibited behavior that there is a vertical asymptote on the derivative function as well. And again, this doesn't stop there. We want to continue this up because you know that your calculator has issues with graphing vertical lines. That's another issue of your calculator. All right. So we can kind of see our picture. Now also kind of looking at the behavior on the other one, since I'm trying to kind of stress graphing as well as finding and evaluating derivatives on the calculator. As x goes to infinity, the end behavior of our graph, the derivative, what are the slopes doing? The slopes, as we come across, we have a really steep positive slope, and then we have a little bit less steep positive slope, and then a little bit less steep slope, and a little bit less steep slope. Okay? This function is a kind of this idea of what's happening to the slopes. The slopes are getting more and more and more horizontal. They're headed toward a slope of 0, the slope of a horizontal line. So when we see this derivative, and you see how it's positive, but notice that we're going down because we're getting less steep, so the slopes are decreasing. The slopes decrease, and notice that they're decreasing exactly where F is concave down. And so we can see that the slopes are getting closer to 0, and we see that we also have a horizontal asymptote of y equal to 0. Okay? So that's kind of one thing, using the graphing calculator to come up with a graph or a sketch of what the actual derivative looks like. It doesn't give us a formula, but it will help us when we start recognizing formulas and working with them. Now, if I want to calculate the derivative, again, we're going to calculate the derivative, and we were interested in the notes. We were looking at it at, go back to the notes. We're looking at it at 4, I believe. So we're trying to find the derivative at 4. So if I want to find that specifically on the calculator, you can kind of go, just so you don't have to type it in again, you can go just grab it again and put it here. And we can change it to be equal to 4. So it's kind of nice that when you already have it in there, because y1 is where I put my function. And notice that it doesn't say x equals x here like I did when I was graphing. I want the specific slope at 4 and hit enter, and we get this 0.25, with some decimals there. Now, remember, this is an estimate. That what it is actually doing is it's taking a look at this graph, and over here at 4, 1, 2, let's go ahead and kind of show what we're doing for our slope there. That over here at 4, 1, 2, 3, 4, here's the point at 4. Here's the tangent line that I'm interested in. So I'm trying to find the slope of this tangent line. Now, how the calculator is finding it is it's picking a point on either side of this slope and then connecting the dot and kind of coming up with its slope. So remember that what the calculator gives you may not exactly be the slope. It's going to be an estimate of the slope. So usually when you see something like what we had on the home screen there, which is we have, let me get that off, 0.25, a whole bunch of zeros, and 5.2. That 5.2 is probably there because it's going to be a round off error. You're a little off because you're picking 2 points on either side. All right, so I would probably say in my notes as I'm doing this and kind of showing you the work for this, that pretty much you would simply say, on your calculator, we don't care on the calculator how you actually did it. You just go f prime of 4. We're going to do approximately 0.25 because we're not sure. It may be 0.25, but we're not completely sure what it's going to be. Okay? Now, kind of we can start thinking about what the actual formula is, because part of what we're doing in the next section is going to be looking at our kind of what's happening, what is our formula for this, and kind of looking for some shortcuts and some formulas, but previewing coming attractions. Let's start at 1, and I'm just going to go by 1 because I just want to see kind of what the slopes are looking like. Then when I go to my table over here, because remember, y1 is going to be the, what did I do? Go to my table set. Let's go by positive 1 because we want to go forwards 1 each time. So let me delete the negative. So when I go to the table, remember that the values here, these are the y values of the function. These are the slopes. And what I'm trying to do is compare the x to the slope to see if I can see a formula. 1 is 1. 2 is a half. It looks like 3 is a third. 4 is 0.25. 5 is 0.2. And hopefully you'll start to see, what are you basically doing? You're doing a reciprocal. And that actually is what the formula is going to be. A little bit later on in this chapter, we'll learn that the derivative of the natural log is 1 over x. But we can use the calculator to kind of see the relationship and kind of work with it now. And the calculator had no problems with that derivative, because when we take a look at that graph, in the where I was trying to find the derivative at 4, that graph was smooth and continuous and has no vertical tangents. So the calculator was perfectly fine with calculating those derivatives. Now, notice that when it calculated the derivative over here, it stopped right there. But remember, it's picking a point on the left and the right of the point of interest, and at some point when it picks a point on the left side, you won't actually have a point, so it just stops graphing. That doesn't mean the derivative stops. That means that the calculator's technique for finding the derivative has failed, and therefore you need to know that this is going to continue going up to infinity. All right, let's take a look at our next one. Next one, we have a little rational function. So we're going to look at y equals, and we're going to change it to our rational function. So we have our top, 3x squared plus 1. And we're going to divide that by 2x plus 5, 2x plus 5. All right, I can take a look at my graph just to kind of see what we have going. All right, so it's a rational function. Now, obviously, we have a vertical asymptote here. And you'll notice, and this is where you got to start not getting confused. Remember, the red graph is the derivative. And a couple of things to notice about this is there's a derivative over here, and you might be like, where's the function? Remember, this is a rational function. It has one discontinuity at -5/2, -2.5. There's going to be a vertical asymptote, but there's supposed to be more function over on that side. We just don't have a very good window. So one of the things when you're using the calculator and working with this is you have to use the calculator and be able to find the function that you're looking at. See, notice here at -5, it's down at -15.2. So the function's hanging out down here. I'm going to go to my window and I'm going to adjust my Y window so that I can actually see that function. Let's try -25. And I also like to change my scale to 5. Let's take a look at that and see if that gives me a good picture. And so now I can see both pieces of the graph. That's the original. And then the red is going to be our derivative being graphed here. And let's talk about each of our kind of derivatives and why they look the way that they do. All right, the first thing to notice, and I'll do it in red since it's in red, right here we have an extrema. We have a horizontal tangent line here on the original function, and then here we have a 0 on my derivative. Same thing, right over here there's a horizontal tangent line, and there appears to be a 0 right there. If I think about my slopes, let's kind of do them in a light blue here, your slopes right here of your tangent line are going to be positive slopes, then 0. So they're positive and going to 0 slopes. Positive heading towards 0, which means that you're decreasing. Notice positive heading towards 0, decreasing. After this section, my slopes over on this side are going to be negative. So I'm at 0, and then they start to become negative and more negative and more negative, and as it gets steeper, it's getting more and more negative, and you'll realize that, oh, that's going to negative infinity. The slopes are going to negative infinity. So we have that same idea that there must be a vertical asymptote at this location on both the original and on the derivative function because of the behavior of the slopes. Now over on this side, when we're looking at the function, our slopes, now even though this is up at the y values are at infinity, the slopes are negative. And they're negative and heading towards 0, which would mean my derivative, my slopes are increasing to 0. Once I hit this point where I have the 0, my slopes over here are now positive. And they don't really appear that these positive slopes, this graph kind of appears to have a slant asymptote. So what I know is that the end behavior of my slopes, as x goes to plus or minus infinity, the slopes f prime are going to have to head to a constant because the original has a slant asymptote. So it's so notice that you see on the derivative here that as you're graphing it, there does appear to be a slant asymptote. Now, I don't know exactly where it is. I'd have to actually do some work and some pre-calculus and algebra 2 work on doing the long division and dividing the denominator into the numerator, getting the quotient, and the quotient will tell me my slant asymptote, and then the slope of the slant asymptote will tell me where the slopes are headed. So you can kind of start making that connection between what we see on the graph of f and what we see on the graph of the derivative. Now, what they had actually asked me to do for this one is they wanted me to calculate. Every single time I go back, it zooms back out on me. So I want to calculate the derivative of y with respect to x evaluated at x equal to -2. So using that notation, I already have it in the home screen, so I'll just come back over here. And remember, the other shortcut is to go function function alpha f2. And number 3 is your n derived, so you can grab it from there. But then, of course, you'd have to go x and then your alpha f4 and grab number 1 for your function. And we're doing it at x equal to -2. So that notation, and I hit enter, and I get this -38.000158. Okay? Now, we're just going to estimate it, and let's go to 3 decimal places because that's what the AP is going to ask you to do. So I just calculated f prime of -2 if I were to come in and label this as f of x. You do want to be careful about using this notation when they have not labeled it as f of x. But if you label it as f of x, then you can use this notation and we can get our approximation. Let's go 3 decimal places, which basically is -38.000 would be what our answer is for that. Okay, probably up here, since I was doing the 3 decimal places, even though I'm 100% sure it's going to be 0.25, but only because I have prior knowledge. On the calculator, I would have actually written down 0.250. All right. Now, let's see what the calculator gives us for the cubic, or cube root right here. Now, I like to look at it graphically because, again, we're trying to make that relationship between the functions and their derivatives. So I'm going to put my x to the 1/3, okay, over here. And we can take a look at the graph. We'll start with that just to kind of, oh, and let's change our window. Notice you can hit on and that should pause your graphing. Let's just do zoom 6. So I have my cube root coming in, my nice inverse of a cubic. And one of the things that you have to kind of get into the habit of is you have a little bit of a danger here that there is a vertical tangent line right here, that it's coming up and it's a vertical tangent line. And nicely, when you look at the graph here, you can kind of see that you're getting that vertical tangent line right here, because you can see that the slopes are getting, they're positive slopes, and they're getting steeper and steeper and steeper, and they get steep really quick, so they shoot straight up out of the screen. So you can actually kind of see that you have that vertical asymptote there. And then notice that as we go this way, it's concave down, which means we're increasing at a decreasing rate, so we're slowing down, and the slopes, the rate of change, is slowing down to 0. So we see we have a horizontal asymptote on both sides of y equal to 0. Now when I take a look at this and I actually type in my derivative, I'm just going to go up and grab it, that nice easy one, so I don't have to put it in again. And we put in our slope at 0. So I do 0, delete the 2, and hit enter. Notice that I got an answer. And this is what you have to be careful of on the calculator. That the calculator, okay, so from the calculator, y prime of 0 equals 100. But this is incorrect. That because it's using the symmetric difference quotient, that the calculator is going to fail because the function y is not differentiable at x equal to 0 because it has a vertical tangent line. So you do have to be wary of the calculator and make sure that you're thinking about what's really happening there. So here down here in F, where it says which of the following are correct and not correct, really it should say which of the previous are correct and not correct, that I was okay really up until here and here, because at the value of interest it was smooth, continuous, and didn't have a vertical tangent line. But here we have a problem. So C is the first one where we have calculator error, that we want to make sure that we do not trust the calculator's answer, because that would be an incorrect answer. The actual correct answer to that would be y prime of 0 does not exist. And we could prove it with the limit definition, but we're going to wait till we get some shortcut rules and really talk about proving this differentiability idea. All right. Now let's take a look at our tangent. So I go back to my y equals, I put in my tangent of x, and make sure your mode is in radians, which I know mine is. Let's do zoom trig, because that's a trig function, so zoom and 7. And we notice that we have a trig function which does have discontinuities at pi over 2 and negative pi over 2 and so on. But we're calculating the slope at pi. And when you're calculating the slope at pi, I'm actually good at pi, that the slope of that tangent line, and you can probably estimate it, it looks like that slope of the tangent line is about 1. Notice your derivative graph that's being graphed here in red, that this function is always increasing, tangent is monotonic increasing. Notice your derivative is positive the entire time. What happens though is as you get close to an asymptote, you get steeper, steeper, and steeper, and so your slope goes to infinity, which makes there be a vertical asymptote everywhere that there's a vertical asymptote on tangent. Right? If I go over here and I take a look at my derivative, again, I'm just going to snatch that and change it so that I have pi, and then hit enter. So it looks like probably about 1. Okay, this is probably an error measurement from the fact that it's using 2 points close by. So up here we would say f prime of pi is approximately, because we're on calculator section of the AP, we'll round to 3 decimal places, so we'll just write it as approximately 1.000. And I do want you to get into the habit that when you, maybe I should do this up here too, that if you're using the calculator is an estimate. It's always an estimate. Use the little approximation symbol when you're doing it. Right? And again, this one was fine, because at x equal to pi, when you take a look at your graph, here's pi over 2, here's pi. I am smooth and continuous, and I am not unusually steep there. So that would be a good derivative to look at. Right? Now let's look at our last one. We have an absolute value function, which of course we know might be a danger because it has a problem of having a cusp. So let's take a look at our graph. Absolute value of 2x minus 6. And then we are dividing that by, what am I dividing by? 4. All right, so we can take a look at our graph, and we see we have our nice V-shaped parabola. And I'm going to change real quick. I don't like my window, so I'm going to go to, let's just do zoom 6, so I can have tick marks every one. So here's my absolute value coming in, and notice that I have the vertex right here at x equal to 3. And what I'm seeing with my derivative graph, of course it's the same slope, everything over here. Do you see how we get this nice jump right here? If I zoom in just a little bit, just so we can see that a little bit better, I'm going to make my y values only go from -2 to 2. And then take a look at it again so that we can clearly see our V-shaped graph with our cusp right here. And then the fact that the derivative, of course it's constant slope over here, will come in, and then you'll have your constant slope over here. Now what you'll notice is that when you do this, of course, is the calculator going to sketch on these graphs your nice holes? No. You'll need to add that part in as part of your knowledge, that there's a jump discontinuity based on that. Now, if I go to evaluate this derivative, so I'm going to quit back out of this graph and then take a look at the derivative here. And we're doing the derivative at 3, so we changed that to 3. and hit enter. Now notice it's going to tell me that the derivative is 0. But remember that that's only because we're using the symmetric difference quotient. That when I use the symmetric difference quotient, that I pick a point on either side. And when I pick a point on either side of a V-shaped graph, and I'm picking a point on either side of the vertex, well, of course the slope is going to be 0. And so that's actually a failure. The calculator is going to say, let's not label it that way. Since I haven't done F, let's just make sure we kind of come in. I would say dy dx evaluated at x equal to 3 is approximately, now it says 0. And then I'm going to go, wait, that's a problem. This is a calculator failure because y is not differentiable at x equal to 3 because of the cusp. It's not smooth there. And so we're going to have to recognize that E has calculator error as well. Okay, that our derivative with respect to x, evaluated at x equal to 3, the actual correct answer should be D and E. Okay. All right, so now what I'm going to do is I'm going to let you kind of work through each of these examples. And what we're basically doing is I want you to graph the derivative of the function using the command where we do the derivative with respect to x of your y1 and evaluate it at x equal to x. So you're going to want to fill in x, your y1 and x, and graph the derivative and think about all the things I talked about in class and see if you can kind of guess and check and figure out what you think the derivative is. Now, based on the one we did for the log up above, I actually already did it, so we can kind of do this one down here. G prime of x, based on the work that we did above, is going to be 1 over x, provided, okay, x is greater than 0. The reason why I'm adding this in is because this is a domain restriction, right? Remember, your derivatives only exist when the function is continuous, smooth, and not unusually steep. So this derivative, it has no derivative for everything less than or equal to 0, but it has a derivative for x greater than 0, and that derivative, we can already tell by looking at the pattern, is 1 over x. And I would utilize, kind of as you're looking at these, utilize your table feature to kind of investigate and look for that pattern. Like for example, when you look at 0.25x to the fourth, we'll do one together and then I'll leave the rest for you to finish. If I do 0.25 and then x, and what are we doing, to the fourth power, oops, I need to delete this stuff. And put my fourth power back in. All right, and zoom 6, it's fine. And take a look at that. So here's my 0.25x to the fourth. And then hopefully, slowly, as it's graphing, we should eventually see our derivative. Now notice that we already talked about this in class a little bit. The derivative of a fourth degree polynomial is a cubic, and we do see that little cubic behavior. Let's take a look at the table. Let's kind of see if we can get some values. I still have it at 1, and I'm going up by 1. And let's take a look at that table. And remember, I want the red because that's the slope. If I put in an x of 1, the slope is 1. I put x2, the slope is 8. Put in the 3, the slope is 27. So right there, you should be able to guess. Let's back up a few here and take a look at those values that we're getting. What function are we basically looking at? Not only is it just a cubic, it actually is y equals x cubed. So we could say dy dx equals x cubed. We could say y prime equals x cubed. Different notations that you could use for your derivative. Okay, so that's what I want you to do for this section, and that'll wrap up this set of notes.